Welcome class, myself Professor D.S. Rai, Head Department of Civil Engineering, BBD, ITM, Lucknow. We will discuss here subject KCE 602 Transportation Engineering, in which we will discuss Unit 4, Lecture 32. IRC method rigid pavement design by IRC 58 2015. References we have taken here is a highway engineering, principle of transportation engineering, pavement design, and of course, IRC 58 2015. Contents of this lecture: typical cross section of the pavement, design as period, traffic consideration, design traffic, cumulative number of commercial vehicle, temperature consideration, embankment soil and characteristic of subgrade and subbase, concrete strength, modulus of elasticity and Poisson's ratio, selection of fractural strength of concrete, selection of design traffic for fatigue analysis. This is a typical cross section of the pavement. Here rebonding layer of polythene, rebonding layer of 30 to 40 mm BC bituminous concrete. Here this is the subgrade, this portion is subgrade, this is GSB layer, this is drainage layer, DLC dry lean concrete, and there is 125 mm thick polythene sheet for the separation of dry lean concrete and pavement quality concrete, and this is the main concrete of course. We have many times discussed about the different layers of the pavement system. One is important here is a drainage layer. Above GSB, a drainage layer is given for drain of water if coming from any sides and provide cut off water from the capillary action. In this cross section all are same things, but here the cement treatment has been below above the BC 50 to 60 mm are laid below the pavement quality concrete. So, both are important. So, now come to the design period and traffic. Design a span for the concrete pavement of 30 years or more. Traffic consideration, each lane of two-lane highway and outer lane of multi-lane highway. Now, design traffic, average daily traffic based on 7 days 24-hour counts as per IRC 9. The annual growth rate has been taken as per code 5%. The cumulative number of commercial vehicle that are here C is equal to 365 A 1 plus R to the power n minus 1 divided by R. So, here C is the cumulative number of commercial vehicles per day, A is the initial number of commercial vehicles, R is growth annual growth rate of commercial volume, n is design period in year. Now, come to the temperature consideration. IRC 58 has prepared a chart, and they have divided the whole country into different part, and they have given average temperature in different segment of the country. So, for design purpose we have to just choose the temperature differential as per table 1 of the IRC code 58 2015. Now, embankment soil and characteristic of subgrade and subbase. CVR of embankment soil placed below 500 mm, that should be the select soil, and the 500 mm select as a subgrade. The effective CVR of subgrade and its K value for the design. Effective CVR has been taken when the in situ CVR and the select soil have a different, a wide variation in the CVR. Then we can choose the effective CVR by a graph. It has been given in the IRC 58 2015 code. Now, we can calculate the minimum CVR should be 8%, and the effective CVR could be calculated based on log base 10 CVR is equal to 2.465 minus 1.12 log base 10 n. Here n is the rate of cone penetration mm per blow. K value for the granular and the cement treated sub base as per table 3 of the code. Here when we say code, that means IRC 58 2015. K value for the dry lean concrete base as per table 4 of the code. Now, concrete strength. The characteristic compressive strength of the concrete FCR is equal to 0.7 into under root FCK, where FCR is the flexural strength or modulus of rupture in megapascal. Target mean flexural strength F dash CR is equal to FCR plus ZA sigma. Here FCR is the characteristic compressive strength at 28 days in megapascal. F dash CR is the target mean fractal strength in 28 days in megapascal. ZA, a factor corresponding to the desired confidence level in which is 1.96 for 5% confidence level for the normal distribution curve. This has been taken from the normal distribution curve, and this is the sigma, it is the standard deviation in megapascal. So, modulus of elasticity and Poisson's ratio, the modulus of elasticity of concrete E is equal to 30,000 megapascal, and the Poisson's ratio has been taken as mu is equal to 0.15. Now, selection of modulus of subgrade reaction. The effective CVR of the compacted subgrade should not be less than 8%, as we have discussed earlier. Now, modulus of subgrade reaction, that could be find out from the table 2 of the IRC code 58. Provide 150 mm thick granular subbase. Now, provide DLC subbase of thickness 150 mm with a minimum 7 days compressive strength of 7 megapascal. Effective modulus of subgrade reaction of combined foundation of the subgrade plus granular subbase plus DLC, that could be find out from the table 4 of the code 58 2015. Provide a debonding layer of polythene sheet of 125 mm micron thick between DLC and the concrete pavement. Here concrete pavement means quality QPC, quality pavement concrete. Now, selection of fractural strength of the concrete. Here the design of slab thickness, 28 days compressive strength of the cement concrete should more than or equal to 40 megapascals minimum. This is the minimum requirement. For 90 days compressive of cement concrete more than or equal to 48 megapascal. 28 days flexural strength of the cement concrete should more than 4.5 megapascal minimum, and 90 days flexural strength of the cement concrete should more than 4.5 into 1.1, that is 4.95 megapascal. Now, selection of design traffic for the fatigue analysis. Now, design period has been taken as 30 years. The annual growth rate, it may be taken as 7.5, or it may be taken as 5%. Two-way commercial vehicle traffic volume per day is suppose A. Now, percent of traffic in predominant direction, suppose it is a 50% of the A, means in both direction the traffic are same, means both are predominant. The total two-way commercial vehicle during design period shall be C is equal to 365 into A 1 plus R to the power 30 minus 1 by R. Now, it is given the average number of axle per commercial vehicle, it is given, that will be 2.35. The total two-way axle load repetition during the design period T will be equal to C into 2.35, because C is the total number of commercial vehicles we have found from here. So, the total two-way axle load repetition during the design period T will be equal to C into 2.35, it is given. Now, number of axle in predominant direction, that we have already taken 50%. So, it will be the T multiplied by 0.5. Now, design traffic after adjusting for the lateral placement of the axle, that is 25% of the predominant direction of traffic for multi-lane highway, and so it will be C into 0.25. This is the design traffic DT. Okay. So, now come to the night time for 12 hours. Night time for 12 hours, design axle repetition will be DT into 0.6, means 60% of traffic during the night time. Meaning commercial vehicle is moving on the highway 60% during night time. So, it has been taken as 0.6. Daytime 12 hours design axle repetition, that is DTT. So, DT minus 1.0 minus 0.6 means that is 0.4. So, the daytime 6 hours axle repetition DTS, that will be DTT divided by 2. So, now hence the design number of axle load repetition for the bottom of cracking BUC will be DTS. Now, design of slab thickness, we have now continuing. So, night time for the 6 hours, night time for the 6 hours repetition, that is NTS, NTS for the 6 hours only. So, NTT divided by 2. Now, percent of commercial vehicle having a spacing between the front axle and the first axle, rear axle unit less than 4.5 meter. It is given and it will be 55%. Hence, night time for the 6 hours, design axle load repetition for the top down cracking TDC analysis of wheel load less than 4.5 meter, that will be equal to NTS multiplied by 0.555, sorry 0.55. The axle load category wise design axle load repetition for the bottom up or top down fatigue cracking analysis are given in the table. It has been given in the table. So, now cumulative fatigue damage CFD, cumulative fatigue damage CFD analysis for the bottom up cracking BUC and top down cracking, that is TDC, and selection of slab thickness. The effective modulus of subgrade reaction of foundation K is equal to 285 megapascal per meter. Now, elastic modulus of concrete, that is 30,000 megapascal. Poisson's ratio of the concrete, as usual, mu is equal to 0.15. Unit weight of concrete, gamma is equal to 24 kilonewton per cubic meter. Now, design flexural strength of the concrete, these all things are given in the code ISA 58 2015. So, design flexural strength of the concrete is 4.95 as we have calculated earlier, the megapascal. The maximum daytime temperature differential in slab for bottom up cracking as per table 1. It has been given in the table of first table of the IRC 58, in which the country is divided in a different part state wise and the differential temperature has been given in the table. We have to just select from the differential temperature from the code. Now, design of slab thickness, because the calculation of rigid pavement design is slightly complicated. So, we have just taken for the example for the design, and the example is given in the IRC code 58 2015. So, now night time temperature differential in slab, night time temperature differential in slab for the top down cracking is equal to daytime temperature differential divided by 2, whatever the temperature given in table 1 of the code, divided by 2 plus 5 degree. So, this will give the night time temperature differential for the calculation purpose. Now, pavement for the option 1, concrete pavement with the tied concrete shoulder with the dowel bars. So, there are many conditions for designing the rigid pavement. So, here the trial thickness of slab is h. Now, radius of relative stiffness, that is L, will be equal to EHQ divided by 12 K 1 minus mu square to the power 0.25. So, beta factor in the stress equation will be 0.66 for the dowel transverse joint for carrying on the TDC analysis. It has been given in the code. Now, computation of bottom up and top down cumulative fatigue damage as illustrated in table 7.2 and table 7.3 of IRC code. IRC code. So, the total fatigue damage for the bottom up and top down is summation of both table. Now, design of slab thickness. The summation of all should be less than 1. If it is not coming less than 1, then trial thickness the trial thickness is not adequate. Increase trial thickness 10 mm more than the earlier trial thickness and repeat whole process till total fatigue damage is less than 1. So, here the table in this table it is given in the our IRC code. So, here is the axle load, single axle load, tandem axle load, tandem axle load, front axle, back axis, all have been given, and we can found the value here by just computing from here to here. And this is the axle spectrum. A spectrum by which we can calculate the loads, and finally, we calculate the cumulative fatigue damage value for the different thickness, and it is given in the code. So, here the slab thickness is given here like 0.24, 24 centimeter, 25 centimeter, 26 and 28 and 29, and see here this is the cumulative fatigue damage for the bottom up cracking case, and this is the cumulative fatigue damage for the top down cracking case. So, here see here the total CFD, total cumulative fatigue is given here, and due to the value has been calculated by this way. This is for the bottom up crack down and this is top down cracking. See here, this is 30.262, 15.713, 6.2621, 0.976, 0.282. In the cumulative fatigue damage for the TDC case will be again here 56, it is means summation of this and this will be more than the 1. So, it is unsafe. Likewise, come to here 0.976 and 1.73 is still unsafe because it is coming nearly 2 point something. Now, come to the slab thickness 0.29. For 0.29, see here this is the value of total cumulative fatigue damage is 0.282, and here for the cumulative fatigue damage for top down cracking is 0.527. So, the summation of 0.282 plus 0.527 is less than 1. So, it is a safe. So, if the summation of both fatigue damage is coming more than 1, then we have to revise the whole process by increasing the slab thickness by 10 mm. at least code is saying that 10 mm should increase while testing the whole process and check it again whether it is coming less than 1 or not. If it is less than 1, it is okay and it is safe. So, this is the pavement option 2. Here the concrete pavement with no concrete shoulder and without dowel bar in transverse joint. So, dowel bar is essential for the heavy traffic to prevent faulting, erosion and pumping at the transverse joint. So, trial thickness of slab H and radius of relative stiffness 1 is equal to ESQ divided by 12 K 1 minus mu square to the power 0.25. Beta factor in stress equation will be 0.90 for the transverse joint without dowel bar for carrying out TDC. So, in this way we can calculate the fatigue damage with a different option, and finally, that should come less than 1. If that comes less than 1, our design is okay and we will go for the further action. So, now the bottom of crack CFD due to real axle plus CFD due to the tandem axle. The top down cracking CFD due to the real single axle plus CFD due to tandem axle plus CFD due to tandem axle. So, total CFD for the bottom up cracking plus top down cracking should be less than 1. If it is not, increase the trial thickness by 10 mm and repeat whole process till total cumulative fatigue damage for BUC and TDC should be less than 1, and cumulative fatigue damage for the BUC is large for the pavement without a concrete shoulder. So, in this way we can check the different option. So, this is the end. Thank you very much. Thanks.